In this chapter, we look at how to solve higher order differential equations. Specifically, we'll be looking at constant coefficient homogeneous linear ordinary differential equations. So the standard form of such an equation, so in the general case, would look like the nth derivative of y plus some coefficient function of x times the n minus first derivative of y plus da da da, all the way down to the first derivative of y itself, and then possibly some forcing function. Now, we're going to be looking at constant coefficient case, and so that means we're going to be looking at the case when each of these is actually just a number, a constant, and that will make life significantly simpler. So when we solve these, we look at the complementary equation or associated homogeneous equation, which looks exactly like the equation that we had before, except now it's equal to 0 instead of being equal to f. So if something solves the original equation, we'll say that it is a particular solution. Because it works for that particular forcing function. And if something solves the homogeneous one, we will denote it with a y sub c, and we will call it a complementary solution. And the solutions of the complementary equation form a vector space. And this is why we've been doing all this stuff where we're studying vector spaces. Also, due to the fact that these equations are linear, if yp is a solution to the original differential equation, then so is yp plus yc. So we can always add something on like that, because it's basically like when we were looking at matrix equations. If you want to solve ax equals b, and you know that a times y is equal to b, and then you add an element of the null space. So if you know that, say, let's call it z. If az is equal to 0, then a of y plus z is also going to be a particular solution, because by linearity, this is the same thing as ay plus az, which is the same thing as b plus 0. And so the way that we find solutions is we solve the complementary equation first. And I told you that the set of solutions forms a vector space. And so, in fact, your complementary solution is going to look like a linear combination of things. Well, how many things? N of them, if it's an nth order differential equation. So the fact that we've got an nth order equation right here is exactly what is responsible for there being n constants of integration, and hence n parts of your general solution down here. So we're going to need a basis for our vector space. So if we have a set of n linearly independent functions, so if we have a set of n linearly independent functions, then that will give us a basis for our solution space. So if we have a set of n linearly independent complementary solutions, then any complementary solution will be a linear combination of these guys for some choice, really for any choice of constants. Now, in practice, how do you figure out what those constants are? Well, those come from the initial conditions. So the initial conditions will allow us to solve for those. And by the same token, you are going to need to have n things in this set right here, or else you may not have a spanning set for the solutions, and that might mean that you might not be able to satisfy particular initial conditions. So if we have less than n, then we won't have a basis, and we might not be able to solve given particular initial conditions. So that's the reason why we need to have n different things in that set. It has to match the order of our differential equation. But we don't use the initial conditions until the very last step. So what we need to do then is first we find the complementary solution, and then we find any particular solution yp. Then we know that the general solution is going to be our complementary plus our particular. So this whole part right here, this is our complementary one. And notice that this guy here gets no coefficient. It just comes by himself. And the very last step after doing everything else is to use the initial conditions to solve for those constants. So that's what we're going to be doing in the next couple of sections. First, we will talk a bunch about how to solve this one right here. That's what the next video is going to be about. And then we will worry about how to find particular solutions later on in forthcoming videos.